Give me 1 second. Okay, so let me just talk about tomorrow for a second here. So tomorrow, asynchronous day, no live classes. I'm going to have two help sessions. One is from 8:30 to 9:30. This one is going over the 2.23 quiz review, but it's not going to be the quiz review worksheet that you guys printed out. I'm going to save that for Thursday, actually. So I'm going to create another one, and I'm going to put it onto the Teams page for Wednesday. So yeah, so because I don't want this, I want to save the quiz review for the time when we're required to be here, but I'm just going to create an extra review sheet and insert it for tomorrow since it's not required. So, but yeah, feel free to attend or not attend and just watch the video, but whichever you prefer. And then from 9:30 to 10:30, I'll have a help session going over the Chapter 1 limits test. I've graded most of the tests. There's still a handful I still need to get to. I hope to get to that during my planning period today. And I think most of the grades are in, but I will enter in the rest of your grades this afternoon. And then I will release those tests so they can see why you got the grade that you got. And then I'll also be reaching out to some of you who I think would benefit from going over the Chapter 1 limits test. Just for those who may want to consider doing a recovery on the test. So yeah, so that's the plan for tomorrow. Again, those are optional. None of these are required. And yeah, I may also decide to record that Chapter 1 limits test review as well. Okay, good. Any questions that you guys have about tomorrow? Okay. So we still have to finish up product and quotient rule. So let's go back to that handout from yesterday, and we'll do more particle motion. Okay. So we talked about product rule, right? Where if we have our functions are going to become more and more complex. Okay. So our graph is going to become more and more complex, which means that usually our derivatives also means that it's going to become more and more complex. But the idea is the same, right? The original graph is always going to have some slope pattern, and the derivative function just helps pinpoint that slope pattern or slope behavior at any point on the graph. So our derivatives will get messier and messier, but it does the same thing as all other derivatives. It's just trying to describe the slope pattern on the original graph. So let's say we have a function that can be represented as two expressions being multiplied together. So we have to go through this product rule. So we basically are taking turns, kind of pairing a function with the other's derivative. So look at, for example, 1. We talked about how I assigned or arbitrarily just assigned my first term that I see as f, and then the second one as g. And I'm just doing power rule whenever I see f prime and g prime for the respective expressions. So to get from f to f prime, I just do power rule. 3x becomes 3, 2x squared becomes 4x, well, with a negative in front. G function, right? Just asking for the original g function, no changes. I just drag that 5 plus 4x down. Back to f, no changes, drag that down. G prime, 4x becomes 4, 5 goes away to 0. So right now, there's no need to, I'm not going to ask you to simplify or clean up. You can leave your derivative in this form. Okay, any questions with product rule? Okay, quotient rule is where if you can, if we have an expression that can be represented as a numerator over a denominator, then usually quotient rule is the way to go, where we can find the derivative of functions that is represented as a quotient of two other functions. Our derivative rule looks a lot like product rule. We still, same patterns as what we see with product rule, but instead of a plus, we're going to have a minus, and then all over the denominator squared. So it's a little more involved because the derivative also has a denominator portion. Okay, so here's example 2. We have a numerator expression over a denominator expression. So the numerator, I'll call f, and denominator, I'll call the g function. So here's y prime. Oh, and also another thing is that you see the d over dx, that just means find the derivative of something. So d over dx, dy over dx, y prime, they all reference they all just mean find the derivative of something. Okay, let me fill out the parts that we're going to have to figure out. So the first slot is we need to figure out what's going to be our f prime, our g function, which is our second graph, minus f g prime all over g squared. Okay, so I labeled everything, so we just have to just fill in the appropriate information here. So f prime, I'm going to take the derivative using power rule of 3x minus 2x squared. So 3x becomes 3, 2x squared becomes 4x. The original g function, no changes. Back to the f function. G prime. So 5 plus 4x becomes just 4. Right, 5 goes away to 0, 4x becomes 4. All over the denominator squared. So this looks messy, but it does the same thing as other derivatives. It's just, this is, if we plug in a number, it'll, if we plug in the value for x, it'll give us a number, and that number is going to tell us how steep the graph is at this point. Okay. So no need to clean up. We can leave our derivative unsimplified. So any questions with?
Can you explain how you got g prime?
Good. All right. So g prime, I'm going to find the derivative of 5 plus 4x. So 5 is a constant, right? So the derivative of 5 is just going to be 0. 4x is a linear function, so 4x derivative is just going to be 4.
Okay, thank you.
Okay. Yeah, constant goes away, and then a linear becomes a constant. So again, simplifying is not required. Later on, we may need to find critical values, which may require us to do a little bit more with the numerator, but right now we can leave our numerator and we can leave everything unsimplified.
And then how do you get G, the bottom, G2 or
Yeah,
whatever?
so the bottom is just the original G function squared.
Okay.
So
My
I'm
bad.
just taking the 5 plus 4x and I'm just putting a squared around it.
Okay, thank you.
Yeah. Okay, any questions there? Now, some students attempt to simplify this. So let me ask you this. If I wanted to, could I cancel these parentheses out? Or one of these out, take away the 2, and there's 2 of them down here, right? So I'll take away 1 and take away one up here. Can I do that? What do you guys think? Yeah, go ahead, Paul.
That was an accident.
That's fine. Anybody have any idea? Like, I mean, these, right? If I want to simplify, can I just cancel one of these out?
I would say yes, but since you are multiplying F prime and G, I'm not real sure.
You're not really sure. Okay. Yes, so I think it is tempting to cancel these out. And the answer is that we cannot cancel these out. But not because of the F prime. There's something that's preventing us from being able to cancel out. Any idea?
Is it because you're subtracting?
Yeah, that minus sign is causing these to be connected in a way where it's not as easy as just canceling out. Okay. And the reason why I bring it up, because I see it so often where students just, they see a bunch of parentheses and they want to just take it out. Now, unless I can factor a 5 plus 4x from the numerator, if I can take a 5 plus 4x from both these terms, then I can cancel out the 5 plus 4x. But this is kind of stuck to that minus sign, so we can't do that here. Now, Jason, I think to kind of help maybe see it a little bit better here, if I had 3 minus 4x times 5 plus 4x over 5 plus 4x squared, notice that I have nothing being added or subtracted around my parentheses. This is fair game. We can take one of the 5 plus 4x out.
Okay.
But that minus sign it just causes a lot of issues where it looks like such a natural thing to do, but I just want to keep reminding us that that minus prevents us from being able to do it. Okay. Otherwise, we're changing the whole overall value, and it's not. We're no longer dealing with the same problem anymore. As a side note, not every instance where you see a denominator do you go through quotient rule. So this is what I mean. If I have y is equal to, let's say, 3x minus 2x squared over x to the 4th, we talked about how with power rule, we can do power rule if the denominator can come up relatively easily. So you see how there's only one term? And when that one term comes up, it can come up as x to the negative 4, and then we just end up distributing that through, and we get something that power rule can handle. But that's only if the denominator has one term. It's relatively easy to bring up. But if I have multiple terms in the denominator, and if I bring it up, it becomes 5 plus 4x parentheses to negative 1. It causes all sorts of issues. Order of operation prevents us from being able to cleanly expand everything out. So usually, if there's more than one term in the denominator, we leave quotient rule to handle it. If there's only one term in the denominator, I tend to want to just bring it up and rely on power rule. Now, having said that, you could go through quotient rule for this, and that's not a problem. But my preference is it's just a little faster if I can just bring it up, go through power rule without having to deal with another fraction. But yes, if there's a numerator and denominator expression, you can always go through quotient rule if you'd like. But sometimes you can avoid quotient rule for a denominator that only has one term. Bring it up, expand, and use power rule instead. So that also adds to the fact that sometimes you have problems that have multiple ways of solving, and multiple ways of solving can be fine, but sometimes I will kind of help direct you to what I think is the efficient or quickest or least complicated ways. But ultimately, you won't get points taken off if you choose a different path, different from the one I prefer. So just to let you know. Okay, let's go to the next page if there's no more questions. Give me 1 second, guys. Okay, let's see. All right, example 3, higher order derivatives where we have to find the third, fourth, fifth derivative. Usually we're not going to have to go beyond the second derivative, but this is just to kind of show that with polynomials, finding additional derivatives is not difficult, and it's actually usually derivatives gets more, each time we go through a derivative, usually the process gets uglier and uglier and becomes messier and messier. But the nice thing about polynomials is that each time you find the derivative, our terms will get less and becomes less complex as well. So kind of want to show that to you and also have you think about why that's the case. Why does it become simpler why do the terms drop and become simpler as we go down the steps? So here's our function. The nice thing here, these are all polynomials. We can do power rule. There's nothing that prevents us from doing power rule. There's no variable in the denominator. There's no radical. There's no parentheses. So we're good to go for every term. So starting with the first term, we bring down the 5, subtract 1 from the exponent. X to the fourth becomes 4x cubed. 3x cubed becomes 9x squared. 16x. Linear becomes a constant. Constant goes away to 0. Okay, so there's y prime. Let's find our second derivative. Power rule again. Oops, 40, it's not 40. 12x squared. Okay, keep going. Third derivative. Power rule again. One last one. Okay, can you point out some things that you notice about this process? What's happening with each derivative?
It's reducing by 1 factor every time.
Okay. And what about the number of terms?
They're decreasing.
Lose one term.
Right. Why is that? Why do terms keep dropping out?
Because a constant is always 0.
Yeah, good. So what if we keep going? What if we keep finding the derivative? Eventually, all polynomials is going to turn into what if we take the derivative enough times?
0.
0, yeah. So if I take the derivative 2 more times here, it'll become 240, next one, and become 0, right? So every polynomial is just going to eventually go to 0, right? Because every degree is going to keep falling by 1. Eventually, if we take enough times, the highest degree will make its way to 0, and by then, all the other terms will be already gone because it will already have turned 0 at the previous derivative. So that's just to kind of show that polynomials kind of have these nice patterns to them. Each of the derivatives just falls nicely, and the pattern is easily, yeah. So in a sense, we call it kind of behaves nicely in terms of it doesn't the derivative doesn't become messier and messier. So if you were to take BC calculus, you're going to see something that they explore. They use this nice property of polynomials to help solve derivatives or help model derivatives of other functions that are more difficult to handle. They take advantage of these properties to solve problems that would otherwise be harder to do. Okay, so this just to kind of show the patterns there. Notations. There's a bunch of notations to represent first derivative. So we've seen f prime, depending on the variable. Sometimes if it's a g of x, we call it g prime. To get from y to y prime, that's a derivative. You've seen dy dx. So dy dx is a more descriptive way of representing derivative. It also means the same thing. It just means find the first derivative. But it's descriptive because you have the variables involved here. So this is saying find the derivative of y with respect to x. And it gives information about the dependent variable. So this tells us that the dependent variable is y. And it also tells us that the independent variable is x. Right now, it's not a big deal. I mean, we just know that dy dx is for first derivative, but later on, we're going to see other information. Sometimes x is not always the independent variable. Sometimes time is the independent variable. So we may have dy over dt, dx over dt. You'll see that in related rates when all of a sudden we're switching over to time being the driving force for our problem. Or sometimes you may see in second semester, we're dealing with the rate of change of population with respect to time. So we'll see P and T. So population P is the dependent variable and time is the independent variable. So you'll see this notation, kind of this structure, and the top variable is the dependent, bottom is independent. It's just kind of like a side note for now, but later on, having those descriptive forms can kind of help move us along in the problem. Right, but right now, we're just kind of recognizing it as derivative, and we can talk a little bit more later, some more detailed information about it. Notations for second derivative, sometimes you just follow the pattern, right? F prime can be written as the derivative will be F double prime, G prime will be G double prime, Y prime will be Y double prime of X, or Y double prime. Another notation for second derivative is d2y over dx2. So this 2 doesn't mean square anything. It means to find the second derivative. So we're not squaring the first derivative when we see this. Okay, we're never going to be squaring the first derivative. So just know that's the notation for finding the second derivative. Third derivative, we just follow the pattern. Oh, another notation for first derivative is d over dx of f of x. So yeah, this also means find the derivative. So a lot of different ways to represent find y prime. All right, I asked you to print out this linear motion problems worksheet. I sent out a remind this morning, but I know it was I sent at 8 o'clock. I know it may be kind of late for students who have printed things out earlier or don't have access to a printer this late. So yeah, so if you don't have it, that's okay. You can kind of just follow along and just put this on a separate sheet. It's not like as if you have to write down the whole problem. But I want to go over number 4 and 7. So I do want to talk about linear or a particle motion in detail before we jump into number 4. So it's similar to PVA, but there's more specific things to talk about. So I decided during first period that I wanted to create a step-by-step sheet. So I don't have this on the website yet, but I figured this afternoon when I get a chance, I'll scan this and I'll put this up under today's links. So you can copy this down, but you can also just kind of follow along and then just print this out for your reference later on this afternoon. Okay, so let me do a step-by-step particle motion, and that way you have everything clear, and then we can just apply these steps as we go to our problems. So when you see the words particle motion, it's specifically referring to motion along a line. Usually we're talking about a horizontal line, but I guess it could be a vertical line as well. Okay. But usually it's horizontal line. So imagine a particle or an object that is sitting on a line, and this particle is very restricted. It can only do 3 things. It can move to the right, which we consider as positive velocity. It can move to the left, which we consider as negative velocity, or it can remain motionless, where that's when velocity is 0. Okay, so there's only 3 things that I can do: stay motionless, move to the right, or move to the left. So over the course of these problems, you're going to be asked different things. It may ask, find the locations where the object is motionless, find the locations when the particle actually changes direction, tell me the intervals when this particle is moving left, find the intervals when the particle is moving right. So all this we can gather by following this process. So the first thing we do is we're dealing with motion, right? So motion is velocity related. So the first thing we do is we take whatever's given to us, usually so we're given the position function, and we find the derivative of position to get to velocity. So we find velocity by taking the derivative of position. Right now, we only know how to use power rule, so we use power rule to find that. Or I guess if it's, I guess we have access to product and quotient rule as well, but for now, we'll just use power rule. The next thing is we're going to have to find critical values. So the next thing is we always want to find when the object is motionless, because if we can find out when the object is motionless, it gives us boundaries for intervals of moving right and moving left. So we're always going to find where velocity is equal to 0. So the first 2 steps are always the same. Get to the velocity function and set the velocity equal to 0. So right now I'm just doing a big overview here, so we're not doing the full example yet. So let's say we solve for t, we set the velocity equal to 0, we solve for t, and we got t equals 4 and 8. So we have 2 time locations when this object is motionless. So now the next step is you're going to create a velocity sign line. So on your velocity sign line, you're going to put down your places, your time intervals where the object is motionless, where the object is not moving. Okay, so right now, don't worry about the. So all we're putting onto our sign line right now is just 4 and 8. Now, having a velocity sign line, it kind of helps gives some visual idea as to what's happening with this object. So this is what's happening here. We know that up until time t equals 4, this object is going to be moving moving the same direction. It's moving to the right this entire time, or it's moving to the left this entire time. Okay. It's not going to change direction at all. It's going to, whatever direction it is, it's going to keep going in that direction. Okay. Now at time t equals 4, this object is going to come to a stopping point. It's not going to move. And then after 4 seconds, it's going to start moving again, and it's going to be in the same direction as well, either moving left or moving right. So we'll have to figure that out. But then it's going to stop again at t equals 8, and then either continue in that same direction, or it's going to turn around and go the other direction. So we have 3 things to determine right now. We have to figure out what is the direction of motion in each of these time intervals. But we can pick any value as long as they fall within these as long as they fall within whatever's in these identified on this number line. So here I can choose 0, I can choose 1, I can choose 2, I can choose 3. All right, so we have a bunch of options, but I'm just going to arbitrarily choose some numbers here. I'll choose 3. To test what the direction of motion is in that first interval. For the second interval, I'll choose 5 to test. And then for the last interval, I'll choose 9 to test. So what we do is we're going to pick a value in each interval, which I just did, and we're going to plug it into the velocity function. So let's say we had a velocity function already sitting there ready for us. We'll take the 3 or 2 or 1 or whatever number you want to choose, but I chose 3. Let's say we plug 3 into the velocity function and I got -6. The value is not that important. It's the sign that's more important. We see it's negative, right? So negative means that this object is moving to the left. So it's moving to the left. I'm going to give an indication of that by putting a negative in that interval. Okay, put a negative in that interval. All right, moving on to the second interval. My test value is 5. So let's say I plug 5 into the velocity function and I got a 1. Right. The important thing is that it's a positive number. So that indicates that this particle, this object, is going to move to the right during this time interval. So I put a plus there. Okay. Lastly, I see a 9. I'm going to choose 9. I plug 9 into the velocity function. I get a positive number that indicates moving to the right. So let's see if we can get this into a visual picture in our head. This object is moving to the left all the way until it hits 4 seconds. When it reaches 4 seconds, it's going to do what?
Go to the right.
Before it goes to the right, though, what's it
Stop.
going to do? Good. Okay. It's going to stop, right? It's going to stop. Then it's going to turn around. It's going to move to the right for 4 seconds. At 8 seconds, it's going to stop, but it's going to continue moving to the right. So I want you to be able to take this out of the abstract form and get it into a visual picture in your head. So now the next question is, find when the object changes direction. Okay, so sometimes you may have problems that's asking you when it changes direction. So we look to see our critical points. These are our potential places where it may change direction. But there's no change in sign here. So there's only going to be a change in direction at t equals 4. So the way we would write it is this object changes direction at t equals 4. Our justification is because velocity changes signs. Other times, the problem may ask you to specify the interval when the object is moving just to the left or just to the right. So I just need to pull information from my sign line and to get it into interval form and to provide justification. So if I'm just reading off of this example, moving left is going to be this entire interval. So from -infinity to 4, because velocity is negative, because velocity is less than 0. And this object's moving to the right from 4 to 8, and then from 8 to infinity, because those are all positive. So positive correlates with moving to the right, because velocity is greater than 0. Okay, any questions here? We'll do a full example now, but I wanted to kind of give an overview as to the steps that we'll be taking as we work through these problems. Can I just make this simpler? Can I just make this from 4 to infinity? Since both sides are positive, there's no change in direction. So can I just make this go from 4 to infinity?
No, because it stops.
Yeah, it stops at 8, right? So at 8, it's neither moving to the left or to the right. So we can't include 8 as part of moving right. So that's why we had to break it up at 8. All right, let's do a full example here.
Mr. Yang.
Yeah.
Why does it stop at 8 again? Like, why doesn't it just keep on going?
Well, I guess we haven't done a full example yet, but let's say we took the velocity function and we set it equal to 0, and then we solved it and we got t equals 4 and 8. So whatever the result of your velocity equal to 0 is going to be where your particle is moving is at a stopping point. So
Okay.
yeah, we haven't gone into the math of it, but we'll do an example now where we're actually finding a value and we're actually putting them onto our sign line. So it could be only one number, it could be 2, just depending on what the result of our equation is. Yeah, but right now I just wanted to give some concrete numbers to kind of help us step through the idea, and then now we'll look at a full example. Okay, so number 4, we have a particle moving along a line for all real numbers, so we're going to include negatives as well. How many times does the particle reverse direction? So, all right, our first steps are always the same, right? Let's find our velocity function, and then let's set the velocity equal to 0, so we can actually begin to populate our velocity sign line. Okay, can someone tell me what the velocity function is going to be? Power rule.
Five t to the 4th minus 20t to the 3rd.
Good. So we have our derivative. We were able to work our way down from position to velocity. We need velocity because we need information about motion, right? So velocity is going to give us information about the motion behavior of this particle. Next step, we need to find our critical point. We need to figure out when the particle is motionless so that we can gather information about our sign line. So we're always going to set velocity equal to 0 for these types of problems.
Mr. Yang, why is it not minus 20t to the 3rd?
Oh, sorry. That's my mistake. Thanks.
You're good.
I left out the t. All right, so we have velocity equal to 0. We're trying to find critical numbers. We can take out a GCF. And we get t minus 4. So we solve for t. What are the t values where the particle is motionless?
Zero and 4.
Yep. All right, is this enough for us to answer the question? Can we just say that 0 and 4 are also where the particle changes directions?
No, because we don't know the signs.
Right, so we need to figure out the signs. So the reason why I bring this up is because sometimes I see students, they stop at this point and they think of motionless as the same thing as reversing direction, or they assume that every time that it's motionless that it's going to change direction. It's possible, right? These are the potential places where it changes direction, but until we test the intervals, we're not going to know for sure. Okay, so we have our critical values, we have our potential values, but we still have to do our test. Okay, so the next step, let's create our velocity function, or sorry, velocity sign line. So I know that each of these, these are all going to be consistent in the sense that this is all moving in the same direction here, same direction, same direction. We should have to figure out which is which. So we're going to use test cases. I'll choose numbers in each interval. Okay, doesn't matter which one you choose, but normally I like to choose small numbers, right? The smaller the number, the easier usually it is to plug in. Now, where do I plug these into? Do I plug these numbers into the position or into the velocity?
The velocity.
Right. We want to find out information about motion. If I plug into the position, I'll get the location, but I won't have any detail about whether it's changing direction or not, right? So we're trying to gather information about motion, so it goes into velocity. Okay. Next thing I want to say is you can choose whether to plug -1 into the original velocity or into the factored form. I prefer the factored form because it allows me to get to the sign quickly without having to do a bunch of calculations and adding and subtracting. I mean, I guess if you have a calculator, it really doesn't matter, but factored form, I think, is the faster way of getting to a number without the messiness of combining a bunch of numbers. So I'll plug -1 into my factored form. So if I plug -1 in for t, this will give me a negative value. -1 in for t here, that's also negative. So negative times negative is positive. So I'm able to quickly gather information about the sign without really having to figure out what that value is. Next up, I'm choosing 1 as my test case. 1 in for t, I get a positive number. 1 in for t here, I get a negative number. So positive times negative is negative. Moving left. Okay, take 5, plug in. That's a positive number. 5 minus 4 is also positive. Positive times positive is positive. All right, what can we conclude here? How many times does a particle reverse direction?
3 times.
There are 3 different directions, that's true, but how many times does it change directions?
Twice.
Twice. Yeah, so reversing, we basically only have to look at the critical values and see if the critical values have opposite signs on either side. If your critical value has opposite signs, then that's 1. Here, that's another 1. So we say 0 and 4. So it does end up that all the places where the object stops is also where it changes direction, but we can't always assume this. Okay, we have to do the work to justify it. Oh, sorry, change the signs. Okay, I was hoping that we would do number 7 as well, but I think you got a big idea, right? From here, if I want to find intervals of moving right or moving left, I can just indicate those parentheses, but everything that I need, I can just pull from what I gather from the sign line. Okay, so maybe tomorrow, not tomorrow, Thursday, I'll continue to do this. I'll do the quiz review, but tomorrow morning, feel free to stop by. I'll try to put together a worksheet for tomorrow morning for the help session. I'll go over some details about the quiz, but again, not required, just want to give some additional resources. All right, thanks everyone. Hope you guys have a great day. I'll see you guys Thursday.
Thank you, Mr. Yang.
Thank you.
Thank you, Mr. Yang.
See you guys. Have a
Thank
great
you.
day. Enjoy your
Bye,
AC
Mr. Yang. Thank you.
Thank you.
Thank you.
See you guys.
Mr. Yang, can I ask a question really quickly?
Sure.